Greetings everyone, thanks for joining me again. Today I'm going to go over my driver isolation results, and that's where instead of using rigidly attaching a driver to a panel with screws or something, we use dampening materials between the panel and the driver, and then if there's whatever we're using to press that driver against the panel, dampening material between there and the driver, so the driver itself is just in a damped little envelope basically, and those forces are not, the vibration of the driver's not being put into the panel. I wasn't originally going to do any testing on this. It never really seemed like that significant of an issue, but I seen comments in a forum by a number of people that were pretty experienced builders, and one that was an acoustic engineer, and the acoustic engineer, if I remember correctly, actually made the claim that it was virtually all of the radiation that you see from the panels that we've seen in my prior videos were the result of the driver driving the panel instead of sound coming from the driver inside the box, and then from the sound inside the box into the panels where it gets radiated out. That seemed a little hard for me to swallow, but the whole reason that I've started doing this sort of testing is I didn't want to just keep working from a theory and sort of hand-me-down tribal knowledge that is so common. I wanted to actually have some data and really see what really these sorts of things actually do. So what I did for the driver isolation is I used, first of all, used a sorbethane gasket. Sorbethane is not just ordinary rubber. If you squeeze it, it kind of takes a number of seconds to go back to its original shape. It's probably the most well-known vibration dampening material that's reasonably well available and somewhat cost effective. It's certainly not cheap like a similar thickness of just some generic rubber would be. It is kind of expensive in that regard. But it is pretty widely available. So that's the gasket, and of course that goes right here. And then on the back of the driver I have a sorbethane button, and you can get these off YouTube. I use them as feet on my speakers and speaker stands. So what's happening here is the little let's see. So I got this little driver box that goes on the outside of that driver, and it had a little stub attached to it to push on the back of that driver right on this nub, right? So now you have this driver fully isolated from the box and from the mounting pressures that are being put on it. And the results are pretty interesting. So here again, just to go over, I'm using my standard box, again, 3/4 inch plywood for this testing, and I take a near field measurement at the side panel and the rear panel, and here is the side panel. Red is the isolated driver, and the blue is just the bare, just an empty box. Empty 3/4 inch plywood box. I think it was 3/4 inch plywood. Anyway, first thing to notice is, it's got a little bit of promise there. The primary panel resonance that I really think is the real issue we need to solve is knocked down 8 degrees, 7 degrees, and or decibels, and it's down to just a little peak versus a fairly wide peak right here. Similarly here, about the same level as the control box, but much more narrow compared to the control box right here. Above here, I'm not really seeing a benefit, and I guess I would have expected a benefit there, but I guess once you get in that mask controlled region, it just didn't really do anything. And on the lower end, I didn't really see any change, and that's good. You don't want to give up performance in one area to gain in another. So rear panel looks good. Okay, side panel. Once again, the main peak is dropped down 6 dB, quite excellent. This lower area is also knocked down, 7, 8 dB. So excellent. Down here, really not any difference. Kind of smoothed out this area for some reason, rather interesting. So that's good. And then once again up here, really no difference. So what we're really seeing for the most part is at the high end, nothing happens. At the low end, nothing happens. But at the primary panel resonance region, which is the most important to me, it's definitely doing something. Now, I would not put it on the same league as some constrained layer damped braces, and I would not put it in the same league as some constrained layer damped panels themselves being used. But no doubt it is doing some good. So then the next question is, how do you do this in an easy to implement way? Part of the focus of all my testing is not just to find good methods, but to find methods that are cost effective, easily available, easily applicable by the average do-it-yourselfer. So what I did was, instead of using the little button, I tested just with the screws like I normally would attach the driver, and with the sorbethane gasket though. And surprisingly, the results were almost as bad as using no gasket at all. So that told me that the screws themselves, by being in contact with the driver frame and the panel itself rigidly, is transferring a considerable amount of energy. So if we still want to make this easy to implement, I thought, well, I'm going to try just little rubber O-rings on the screw so that the driver was only attached to or in touch with the sorbethane gasket still and rubber O-rings. The screws themselves were no longer contacting the driver frame because we were using those rubber O-rings. And how did that do? Well, here's the rear panel, and the convention I've used here is easy driver isolation method is the method I just described. Full is the first example where I use sorbethane gasket and the sorbethane button. Not so easy to pull off. Looking at the lower peaks, I'm pretty happy. The easy method is actually lower than the other two. About as wide as, no isolation. And then the upper peaks, the easy method tops out about right there. So we are gaining, 5 dB off the top there. So that's pretty good. Still a little bit higher than the full driver isolation for sure. But I would note also that it's just this little peak, just like the full isolation, right? It's not this much larger area spread over wider frequency range, more likely to be heard. So I would say we're getting most of the benefit of full isolation. Going to the side panel, and we see pink as the easy method, pretty much on par with the other ones. Stays down low right here, just the same as the full isolation, so very promising there. And then tops out about right there. So we're only gaining 2.5 dB about right there. And then drops down significantly, just like the full isolation. So overall, even the easy method is worthwhile. Now, the next question I had was, if I applied this method to a constrained layer damped panel box, would the CLD box itself just kind of swamp the effects of this because it's so good at dampening that you wouldn't even really see this? So I did apply it. So here's the results of using driver isolation with a box that's been built with CLD methods. And this is the rear panel. Driver isolated in red, no isolation in blue. So I would call this a wash. And the isolated, you know, nice 3 dB. It's cutting off the main resonance, and it's a narrower resonance, so that's good. So a little bit of benefit at the rear panel. Looking at the side panel, and here, you know, quite a bit more significant. I mean, we're knocked down 3 to 5 through this entire range. And I should point out, if you can remember some of those earlier plots of empty boxes, since some of the early CLD stuff, you know, you've got some stuff going on up like this. And with this box, look where we're at. And I will be going over this particular box. It was basically a demonstrator of a number of these, of pretty much what I've learned so far in all this testing. And the last little bit was to test this driver isolation. And I mean, I must say, that's just knocked it. At this point, I don't think anybody could say you could even possibly hear that when some of those other ones are probably up in here. So, driver isolation works, and it works right in the area that I'm most concerned with, which is those primary panel resonances that are so close to the nominal driver output itself. And it even works with a box that's been built with CLD in the first place. And it's super easy to do. Get a decent rubber gasket, sorbethane if you can, but you know, if you can't, maybe try like 1/8 inch thick rubber, and then O-rings. I just got O-rings from the hardware, Ace Hardware store. They're made out of Viton, which itself is actually usually used when you want a rubber. It's reasonably cheap rubber that does really good vibration dampening. Viton is one of those rubbers. Those O-rings are made out of Viton. Work pretty good. Now, where would you use this? In the low frequencies, if you had a dedicated woofer and it's not running up into those primary panel resonance region area, I don't think you would use this. I mean, it doesn't look like it makes things worse. Some people have pointed out that you should have a woofer for bass rigidly mounted to the box, and that there's benefits to that. I don't really know all the theory behind that or the data behind that, but it doesn't sound unreasonable to me. But if you have a pure mid, it almost seems like a no-brainer, because it helps right at that primary panel resonance region. Now, if you have a woofer that's doing both jobs in, say, a two-way, it's a little tougher. I'm not real sure. I have to do more research on that and understand the argument for having something rigidly attached at the low frequency region versus the benefit that you get here with that higher up mid-range primary panel resonance region. But anyway, thanks for joining me, and I hope you got something out of that. Thank you.